Hi, everyone, and welcome to the very last note video that you're going to have to watch this year. Congratulations, you did it. This last video is going to be on electrochemistry. Electrochemistry is the branch of chemistry that relates electrical energy and chemical energy. We have previously talked about redox reactions, but we're going to go more into detail with that. So an oxidation reduction or redox reactions are the heart of electrochemistry due to the motion of electrons, which we know is what electricity is. Redox reactions occur in half reactions, an oxidation reaction and a reduction reaction. Oxidation occurs when an atom or ion loses electrons, becoming more positive. Reduction reactions occur when an atom or ion gains electrons and it becomes more negative. So, for example, we've got two half reactions here, the oxidation of iron to the iron +3 ion. Okay, so iron oxidation is loss, so iron will lose 3 electrons to become the iron +3 ion. Reduction of oxygen gas to the oxide ion. Okay. So before I go on that one, let's just talk about this half reaction, and we want to make sure that it's balanced. So you balance half reactions by having the same charge on both sides and the same number of elements on both sides. So I've got 1 iron on each side. On the left side, I have a charge of 0. On the right side, I have a charge of 0 because the +3 and the -3 give me 0. So that thing is great. For oxygen reduction, so it's going to be gaining an indeterminate number of electrons that we will determine in a second, and it's turning into the oxide ion. Well, right off the bat, I have 2 oxygens on the left. I only have 1 on the right, so I need to put a 2 there. Now to balance the charge, there's a -4 on the right side from the 2 -2s, which means I need 4 electrons in this case. Okay. So that would be an oxidation, so it's losing electrons, and then the bottom one, reduction, it's gaining electrons. So the reducing agent is a substance that reduces another compound by undergoing oxidation. The oxidizing agent is the substance that oxidizes another compound by undergoing reduction. So they're opposite. The reducing agent is the thing that's oxidized. The oxidizing agent is the thing that is reduced. Now, in order to help us remember where the electrons go, or what electrons do here, oxidation is loss, reduction is gain. That's oil rig. Okay, remember we did talk about this before. So you got oil rig, or you have Leo-Szilard. Loss of electrons is oxidation, gain of electrons is reduction. And if you don't remember us doing this previously, we went and did that in the chemical reactions module, which I think was 5. I'm not sure, 5 or 6. In order to determine if a reaction is a redox reaction, you have to determine the oxidation numbers. The oxidation number is the real or apparent charge of an atom or ion has when bonds are assumed to be ionic. So there are rules for determining the oxidation numbers. Pause the video here. Make sure you have these written down because you're going to need them. So let's go through these examples and do the oxidation numbers for each element within them. So oxidation numbers have to add up to be their charge. And so this has to add up to be -1, okay? Because the charge is -1 for the ion. Oxygen, always -2. That's rule number 3. There's 3 of those, so that gives me a -6 for my total. In order to make it a -1 charge overall, this needs to be a +5. There's 1 nitrogen, so that 1 nitrogen has an oxidation number of +5. Remember, when we do this, I do the oxidation numbers on top, and below gives me the total so I can help figure everything out. Okay, magnesium bromide. I know it needs to add up to be 0 because it's a neutral compound. There is a rule for magnesium. The oxidation number for group 1, group 2, and aluminum are +1, +2, and +3 respectively. Magnesium is in +2, so that's in the second group. So that's +2. There's 1 of those, that's +2. This has to be -2 to give me 0. There's 2 of those, so each one is going to be -1. And finally, the ammonium carbonate. We can do this separately. We know ammonium has to be +1. And then that will give me ×2. And then I know the carbonate will be -2, which those guys added up will give me 0, because that would be +2 and a -2. So we know hydrogen's +1. There's 4 of those, so that's going to be +4. If this needs to be a +1, this is going to be -3. There's 1 nitrogen, so that 1 nitrogen is -3. For the carbonate, we know oxygen's -2. There's 3 of those, so that's -6. The total has to be -4, so this is +4. There's 1, so it's +4. Okay, so that's doing it separately. Then we can determine if a reaction is going to be redox or not by doing it for the whole equation. And remember, not every reaction is a redox reaction. So don't worry if you can't get some to work. Remember, either one thing gains and one thing loses, or nothing changes. If you have 2 things gaining, 2 things losing, you've done it wrong. So chlorine, that's its elemental state. It's going to be 0. Bromine or hydrogen's +1. So that means bromine must be -1. Again, hydrogen's +1. Chlorine's -1. And then bromine in its elemental state will be 0. And so what changes? Chlorine goes from a 0 to a -1. That means it gained 1 electron. The bromine went from a -1 to a 0, so it lost 1 electron. So let's see, the chlorine was reduced because it gained electrons, so that makes it the oxidizing agent. Bromine was oxidized, which makes it the reducing agent. Okay. The next one, oxygen, we know is going to be -2. That's -4. Overall 0. That must be +4. Chlorine and hydrogen. Chlorine is going to be -1. That's -2. So the manganese is +2. That chlorine is 0. -2 +1. So what changes? The manganese goes from a 0 to a it goes from a +4 to a +2, so it gained 2 electrons. And then the chlorine went from a -1 to a 0, so that means it lost 1 electron. So manganese was reduced because it gained electrons, which makes it its oxidizing agent. And the chlorine was oxidized, which makes it the reducing agent. And then for this final example, I'm just going to write it again, just for a little more room. Okay, oxygen -2, that's -6. To be 0, this is +6, so that iron is +3. -2, +2, 0, -2, +4. So iron went from a +3 to a 0, so it gained 3 electrons. Carbon went from a +2 to a +4, so it lost 2 electrons. So that means iron was reduced, making it the oxidizing agent, and carbon was oxidized, which makes it the reducing agent. Wonderful. Okay, so that was all review. We should have known how to do that. Now this next one, balancing by half reactions, may or may not be review. I don't remember if we did this or not, but so when balancing by half reactions, the first thing that you want to do is go through and give everything their oxidation numbers. So this is +3, this is -1, that's 0, that's 0. Next, we want to figure out what's being oxidized and what's being reduced. So gold, let's see, gained 3 electrons. Iodine lost 1 electron. So now what I want to do is I want to write these separate half reactions. So I want to take the Au plus 3. We said it gained 3 electrons to turn into solid gold. Perfect. And then the I minus lost an electron to become iodine. Once I do that, I then want to balance them separately. So I want to make sure you have the same number on both sides, and you want to have the same charge on both sides. So that top equation, the one with gold, it's got 1 gold on each side. The left side has a charge of 0. The right side has a charge of 0. For the bottom one, I'm going to need to put a 2 here to give me 2 iodines on both sides. And then I'm going to have to put a 2 for the electrons so that I have the same charge on both sides of -2. Once, and then I'm on step 3, once the individual reactions are balanced, you can add the 2 reactions algebraically so that the electrons in the 2 half reactions cancel. Okay, so in order to bring our 2 half reactions together, you have to have the same number of electrons. That's the key. So I'm going to multiply the top one by 2 and the bottom one by 3. Okay, and then when you bring them together, things on the opposite sides that are the same will cancel, and then you just write what you have left. 2Au plus 3 plus 6I minus gives me 3I2 plus 2Au. And you are balanced. That was an easy one. Let's do a harder one. Okay. Balance the equation by the half reaction. So again, we're going to go through and give everything their oxidation numbers. See what changes. Manganese goes from a +4 to a +2. So I gain 2 electrons. And then chlorine goes from a -1 to a 0. So it lost 1 electron. So let's see. It says here, critical information, if you are working with an aqueous solution, you can use the ion of interest when balancing the half reaction. So for example, hydrochloric acid is an aqueous solution. So I only care about the chloride ion. So technically the chloride ion is the thing that lost an electron to become Cl2. And then for the other one, the manganese 4 oxide, since it's a solid, you have to keep it together. It gains 2 electrons to turn into, and I can just do the manganese +2 ion here because the manganese chloride is an aqueous solution. Now I have to go through and balance each one. So to balance this one, I'm going to put a 2 here and a 2 here. That balances the number of chlorines on both sides and the charge on both sides. For the bottom one, I have 1 manganese. I have 2 oxygens. When you do this, you can use hydrogen ions and water to help balance. Okay, so I can add, and how do I know I have water? Well, water is right here as a product, but also there's aqueous solutions, so water is available. So I'm going to put 2 waters over here to give me 2 oxygens, but then I've just made another issue. Now I have 4 hydrogens on the right that are not on the left, and that's okay. I can add 4 hydrogen ions because I am in an acidic solution. So the only thing that you need to look at now is to make sure that the charges of the are the same on both sides. So on the left side, I have a +2, and on the right, I have a +2, so that's great. So now all I need to do is bring these 2 equations together as long as they have the same number of electrons, what they do. So that can go away, that can go away. So this is where it gets a little bit wonky. You'll notice that there was 2 chloride ions here, there's 4 hydrogen ions here, and 1 manganese +2 ion. Well, the reason why there's 2 chlorides here instead of 4 is because we kind of did a net ionics by only looking at the ion that we cared about. and there would have been the 2 chloride ions here that will come together to give me the manganese chloride. So what that means is that you're actually going to have the 4 hydrochloric acids plus 1 MnO2 gives me, I'm going to have 1 MnCl2. I'm going to have the chloride, the chlorine gas, and then 2 H2Os. Okay, so that's where the other 2 chloride ions went. It went to go form here, so that you'll come together to get the 4 hydrochloric acids, the manganese 4 oxide, the manganese 2 chloride, chlorine, and 2 waters. And if you look at it, you can tell that it's balanced. 4 hydrogens, 4 hydrogens, 4 chlorines, 2, 4 chlorines, manganese, manganese, 2 oxygens, 2 oxygens. So there is your balanced equation. And we did that by half reactions. Okay, one more here. Going to do the same thing here. -2, +4. Oops, not 0. -2 + 1. Okay, so for the HNO3, do it over here so you can see. The nitrate must be -1. That's -2. That must be +5. So it's going to be +1 +5 -2, -2 +2. So what's changing? This nitrogen here is going from a +4 to a +5, so it lost 1 electron. But then this nitrogen also gained 2 electrons. So it's actually doing both. Let me show you how this works. So since they're a gas, we have to leave it together. So the NO2, it's going to lose an electron. And again, we're an aqueous solution, so I'm just going to look at the nitrate ion. Balancing it out, I'm going to add, I need a water over here. So that gives me, so then I'm going to add, let's see, 2H+ over here, and then it should be balanced. Okay. Then for the other one, where it's gaining electrons, so NO2 plus 2 electrons gives me NO. I need to add a water over here, 2 hydrogen ions over here. Perfect. Now, in order to bring these together, they have to have the same number of electrons. So I'm going to multiply this top one by 2 to give me 2H2O plus 2NO2, 2 electrons plus 2 NO3 plus 4H+. So like we said, if they're on opposite sides, they cancel. These 2 hydrogen ions cancel out with these 4 to give me 2 here. This 2 water cancels out with this water right here. And now let's see what we have. So we have H2O plus 2 NO2. No, I'm sorry, there's 2 here and 1 here, so 3. To give me, we have an NO over here, and then I have 2 hydrogen ions and 2 nitrate ions to give me 2 nitric acids. And there is your balanced equation by half reactions. Okay, and then the other part of this is talking about electrochemical cells. So electrochemical cells are devices that can either generate electrical energy from a chemical reaction, which are known as galvanic cells, or facilitate a chemical reaction through the introduction of an electrical energy, which is an electrolytic cell. When the oxidation and reduction half reactions are physically separated, it makes a galvanic cell. Each half reaction occurs on the surface of an electrically conductive solid called an electrode. There are 2 electrodes, the anode and the cathode. Each electrode is immersed in a solution containing ions needed for the half reaction. The electrodes are connected by a wire so that the electrons can move from the oxidation half reaction to the reduction half reaction. The solutions are connected by a salt bridge so that the ions can move between solutions. In an electrochemical cell, the chemical potential energy can be harnessed as the substances undergo oxidation and push electrons through the wire to the substances undergoing reduction. So for example, here is a galvanic cell. You have a copper electrode in a solution of copper 2 sulfate. Over here, you have a zinc electrode in a solution of zinc sulfate. You've got a salt bridge. And the salt bridge you can think about like a switch. If there isn't there, there's nothing for the circuit to flow, because that's pretty much what you're making here. So this is what a galvanic cell looks like. So if we go here, the anode is the electrode in the electrochemical cell where oxidation occurs. And to help us remember, we say anox. Lots of animal-related things in here. So anox. Anode is where oxidation occurs. Oxidation is loss. Okay, so for our example up here, the zinc is the oxidation. So it's going to lose 2 electrons. Notice that the zinc is being oxidized, it's losing electrons. So what happens as the process goes on, the zinc anode is going to get smaller. So this zinc electrode will actually dissolve into solution so the electrons can flow from the anode to the cathode. And then the copper one, where the electrons are going, ends up getting bigger. So copper is the cathode, where reduction occurs, and we use REDCat, reduction cathode. So copper here will be gaining 2 electrons to form the solid copper. So you can see how this would be gaining mass. This is being broken down and losing mass. And the salt bridge moves ions to maintain electrical neutrality, okay, to help us have the circuits flow. And then FATCat is to help us remember how the electrons flow. They flow from the anode to the cathode. So when we're going to actually calculate how much energy, voltage, that these cell potentials have, what we do is we look at this, which is in the notes. It's a standard reduction potential table. So it's all reduction potentials. In a redox reaction, there is a reduction and an oxidation. So please do keep that in mind. So what you do is you look at your redox reaction for the 2 things that are involved. The more positive value is reduced and the other one will be oxidized. So you need to flip the equation of the least positive value as well as the sign for the cell. So the E cell, to calculate the voltage of the electrochemical cell, it will equal to the energy of the oxidation half reaction plus the energy of the reduction, E-ox plus E reduction. So here is an equation. We want to calculate the potential energy we want to calculate the energy from the cell. So first thing I'm going to do is write my half reactions. By the way, this is not balanced, but whether it's balanced or not doesn't change the voltage when you do this. So aluminum is going to be gaining 3 electrons. So Al plus 3 electrons gives me the aluminum solid. And then the magnesium will be losing 2 electrons to become magnesium plus 2 ion. Oh, excuse me. So we need to look at our table. So we go over here and we try to find the one for aluminum gaining 3 electrons, which is right here. And that voltage is negative 1.66 volts. Now we know for the magnesium, that is being oxidized. It's losing that electron. So we're going to find the one for magnesium, which is right here. And what I'm going to do is I'm going to flip that sign. So it's going to be positive 2.37 volts. So that's the E0 cell for the reduction. No, it's just the E0 for the reduction. And this is the E0 for the oxidation. So now to calculate it, the E0 for the total cell, so the standard energy of the cell is going to be equal to the oxidation plus the reduction. You do that math and you get 0.71 volts. So that's how much potential electrical voltage will happen when you build this galvanic cell. Okay. So this question was easy because it told us which one was being oxidized and which one was being reduced. For this next one, it's asking us to calculate the voltage of a cell with silver and sodium in their solutions. So we have to go over here and look, well, here's silver. So I'm going to write it over here. No, what am I? Not plus 2. Ag plus 1 plus an electron gives me solid Ag, and my E naught is 0.80 volts. The next one is the one for sodium. So we got to find sodium. It's all the way down here. So then Na plus an electron gives me the sodium. My E naught is negative 2.71. Now, the rule was the most positive one is reduced. So this is the reduction. So what I'm going to do is I'm going to flip this. And then I also flip the sign of the oxidation. So now if I want to calculate the E naught of the cell, it's going to be the E ox plus the E reduction, which gives me 3.51 volts. And that's it. That's how you do that. And so make sure you have a copy of the standard reduction potential table saved on your computer or somewhere near you so that you can reference it when you're doing this stuff, working on the practice and the quiz that will be going along with this. And then the last thing is an electrolytic cell, which is non-spontaneous. It requires energy. So you'll notice this is different because it is a battery is included. There are a few things to notice that are different about electrolytic cells. Energy is being added. That's the biggest difference. It's not being produced, it's being added. The compound is being split to make elements rather than being combined. And then the electrodes are inert. So electrolytic cells are used for things like plating or recharging other things. So there's only one type of problem we're going to see with this. And it's basically either how long does it take to plate this amount of stuff with this amount of energy, or how much can be plated after this amount of time with this amount of energy. So this question wants to know how many grams of gold can be plated after 60 minutes in a cell with 2 amps. So you either start with mass and go to grams. No, mass is grams. You either start with mass and go to time, or you start with time and you go to grams. So we're starting with time and we're going to grams of gold. So I'm going to start with 60 minutes. I'm going to take those minutes, turn them into seconds. The reason why I want to turn them into seconds is because an amp, which we know we have 2 amps, is a coulomb per second. So what I'm going to do, I'm going to say 2 coulombs for every 1 second. So these problems are just long dimensional analysis problems. Then I'm going to use Faraday's constant, which is 96,500 coulombs for every mole of electron. Coulombs cancel. Okay, now I'm trying to go from moles of electrons to moles of gold because I want grams at the end. To do this, you need to look at your standard reduction potential table and find the one for gold and see how many electrons are being transferred. You can see here 3 electrons will be transferred to give me 1 mole of electron will give me 1 mole of gold will give me 3 moles of electrons. And then finally, we just need to take moles into grams. For every 1 mole of gold, it gives us 196.97 grams of gold. Do that math, put it in your calculator. Your final answer, 4.9 grams of gold can be plated in that time. If you want, it's technically 1 sig fig from that. So you could say 5 grams of gold. This one has 2 sig figs, so it's whatever. Okay. And that's it for electrochemistry. Okay, those are your things. So being able to do your oxidation numbers, determine what's being oxidized, what's being reduced, balance by half reactions. We're going to do more of the simple ones like that first example than those more complicated ones. Be able to determine the voltage from a list of standard reduction potentials, and then be able to do a conversion like this for an electrolytic cell. Okay, that's it. Yay being done with notes for the whole year, and congratulations, you did it. I will see you later.